All right, so we have Corrado from the REDTOP collaboration that is going to give us an update on our project. Corrado, the floor is all yours.
Yeah, thanks, Pascal. So,
Maximize. Yeah, it's fine. Basically, see if it's something.
can I go ahead?
Yeah, you can start.
Okay, so this REDTOP is a super ETA factory. We are on the other side of the ledger here. Very low energy, super high intensity. This presentation was prepared by Vito Di Benedetto and myself. Guess who did most of the work? And it's not the speaker, so. Okay, first of all, why you want to, I mean, these days everybody wants to make an experiment that's super, very high energy. Why do you want to try a low energy eta prime factory? Well, the reason is more or less explained in the slides. We know that the standard model is broken, and we are trying to understand how to fix it. At the moment, I think we have no idea where new physics is. So if you would explore the entire physics scenarios, it's probably something like 40 order of magnitudes in terms of energy, which is really impossible. So you need to make an ansatz. And the ansatz that the theorists are making these days is that the dark matter is cold. It means that it has thermalized with the rest of the universe. And this restricts the search for us to about 7 order of magnitudes in terms of energy, from the keV to the TeV, more or less. So the problem is that most of the searches at high energy above the GeV already have indicated that there is no physics there. The space of parameter has not been completely covered, but we are almost there. And also, I mean, we cannot go above about 100 TeV because that violates unitarity. If you go at the even lower energies, there are a lot of bounds from cosmology, astrophysics, and so on. There is only one region, which is mostly unconstrained at the moment, and that's between the MEV and the GeV. If a new physics is there, theorists are telling us that it has to be neutral under standard model charges. Namely, all the standard model quantum number needs to be 0. There are only two particles, let's say, it's in the standard model, at least that we know, that have this characteristic, and that are the eta prime mesons, the Higgs bosons, and the vacuum. Any other particle we know has a charge. So the eta and eta prime also have a very special way of decay. In particular, the strong and electromagnetic decays are forbidden at the lowest order by a certain number of symmetries, which means that more rare decays, possibly induced by new physics, have a larger probability to happen. So in other words, an eta prime factory at the moment can be considered as a low energy Higgs factory, and it's also an excellent laboratory to probe new physics exactly in that small region which is left unconstrained. So REDTOP can do a lot of physics measurements. Let me stress which are the key points here. So first of all, in order to probe new physics there, you know that new physics will be very faint. It comes with coupling constant of the order of 10 to the minus 9 or smaller. It means that you need something like 10 to the 13 or 10 to the 14 eta meson produced. This is a 5 order of magnitudes compared to the existing world sample. And we can do it in 3 years of run. Just to give you an indication of the intensity of this experiment, REDTOP will reproduce the existing eta world sample in just 20 minutes of running. So if you autoproduce the eta prime mesons, you don't need much of a beam. 30 watts and 55 watts of a beam is good enough. 55 for the eta prime, which is a larger mass. The experiment is designed expressly to search for BSM physics beyond the standard model physics in the MEV-GeV region, and the detector is sensitive to resonances very low in energy. In particular, the 17 MeV resonance, which was found a few years ago in Hungary, and that, I mean, we still don't know what it is. It's a medium-sized experiment, and it will cost less than 100 millions. It goes up if you add the contingency and LEAP. There are 6 golden channels that REDTOP could do extremely well, and they will test either discrete symmetries, conservation of discrete symmetries, or they will search for new particles and forces. In terms of testing of discrete symmetries, CP invariance is very important. It's one of the things that we know must be there, and the standard model does not account in enough amount at the moment. We can do that in 2 ways, either looking at the eta decaying into 3 pions, that's called the Dallas plot. Standard model wants that plot is completely symmetric. If you find any asymmetry in the plot, that's an indication of new physics. You can also, if you can measure the polarization of the muon, and that's possible in any decay of the eta into 2 muons and something else, like a pi 0 or a gamma. That's also a straight indication of CP violation behind the standard model. You can search for the dark photon. Everybody, a lot of collaborations are doing that at the moment. It wasn't found yet. You can look for the QCD action, or in general for action like particles. You can search for a dark scalar also, something similar to the Higgs, but which couples to dark matter. You can study lepton flavor universalities also, which is something LACB has indicated that probably is violated. So this is all you could possibly do with the 10 to the 14 eta mesons. It's the fields are grouped in what you can do. Basically, it's 6 possible research programs. You can study discrete symmetries. You can probe for new particle and forces. You can study other discrete symmetries other than CP and CP, like, for example, lepton flavor violation, lepton flavor universality. You can do a lot of precision measurements, like that of the proton radius anomaly. Let me tell you that all the leptonic decay modes of the eta are unseen at the moment. I think Atlas has published something very recently, the eta into 4 muons. You can do also a lot of bread and butter physics. I mean, nuclear models, nothing new, but it's high precision measurements which are badly needed by QCD experts. REDTOP is the only experiment, along with SHIP and recently from HAS, which is a newly proposed ETA factory in China. So it's the only experiment sensitive to all 4 portals connecting the standard model with the new physics. So this is a sketch of a REDTOP. You see it's 2.4 meters in height or diameter and less than 3 meters in length. So it stays basically in a room. It's small, but it carries a lot of technology. And the reason why is because the interaction rate at REDTOP is probably the highest among all the new experiments existing or being designed. You got a few components. There is a vertex detector near the interaction region. Then there is a central tracker, which is made on, it's all silicon here. There's a time on flight, chunk of time on flight, and then a triple readout calorimeter. This is the cost of that we have calculated a couple of years ago. As you see, the detector itself will cost about $55. If you add contingency, you go up to 82. If you add labors, maybe 150 million. So not much. So the cost optimization is still in progress, and it's based on the new sensitivity studies, which are ongoing with the current 2025 Montecarlo campaign. It's a small collaboration at the moment, but still it counts 138 collaborators from 62 institutions. It's not approved yet, so we are trying to strengthen the physics case, and this Montecarlo campaigns will also help with that. So this is, let's go to the computing part of the experiment. So this is what we expect from it. Essentially, we will have also a megahertz, I'm sorry, a gigahertz of interaction rate at the level 0. You know, it's here, it's 700 megahertz. It's about 40 times LHCb, which is probably the experiment at the moment with the highest interaction rate. So you cannot possibly acquire all that stuff, also because we are interested in rare decays. So you need to throw away a lot of events. We'll do that through 3 levels of triggers. 2 are in hardware and 1 is in software. At the end, what we'll be keeping is something of the order of the megahertz, which corresponds to, you know, not much in terms of storage. And that's because the event is very small. It's 1.6 kilobytes. We are calculated how much storage we need, including Montecarlo. We need about 1.5 petabyte a year. Since we went around for 3 years, let's say this is about 5 petabytes and a 5 petabytes experiment. How much CPU we need for reconstruction analysis in Montecarlo? We also calculated that thanks to the experience we're having with on the OSG. We will need about 120 million core hours, 90 million, I mean, that's for the Montecarlo, and another 90 million for the reconstruction job. More likely, what we will need is 70 million core hours a year, maybe more. So we have an ongoing Montecarlo campaign. This is very important for us. The reason why is because there was a laboratory in Germany very interested in us in REDTOP. So they asked us to submit a proposal, but they don't have the beam we want. So we had to redesign the detector and the experiment in general to cope with the lower beam. And this is, so we need to recalculate all the sensitivity to new physics. And this is what we are doing now. Let me stress that also CERN had offered in the past a lower beam, and we decided to look for another laboratory. So if this Montecarlo campaign is successful, it means that also CERN could be reconsidered as a hosting laboratory. So this is our simulation scheme. We have a event generation. We need to generate about 150 billion events, and we do that with GenieHat. Then we use Gen 4 for the simulation of and the propagation of the final state throughout the detector. The reconstruction and analysis completely in Java. And that's based on the LCSIM framework, which was designed as SLAC for the ILC. So this is our architecture. So GenieHat, we sent to GenieHat, we require GenieHat to generate 20,000 events per job. Usually that takes between 2 and 8 hours. Not much memory, 1.2 gigabytes. The output is only 70 megabytes. Giant and the reconstruction, we run it within the same job. We send to Giant only 5,000 events at a time. It takes between 1 and 3 hours. The memory is, you know, below 700 MeV. So I was impressed by the previous talk that requires tens of gigabytes of memory to run. We stay usually below the 1 gigabyte. So the 3 levels of trigger and the reconstructions also are done after the GM4 is done. We process 5,000 events in 15 minutes, takes less than a gigabyte of memory. The output is only 3 megabytes, and that's the beauty of the triggers. So we do our entire processing on the OSG. And this is how we fare in terms of CPU hour, wall hours, and number of jobs that are processed on the OSG. Last year, we were almost first in all the categories. This time, we went down. Still, we have double the number of wall hours, the number of jobs, and the double of core hours. The efficiency is pretty much high, close to 90%, which is, I think, is pretty good. It means that the software is extremely stable. So there are a lot of other. So we are not the largest users anymore. Let me stress the fact that REDTOP is a proposed experiment. We have 0 funds. And it's nice to see that most of the experiments are running now, and they're taking most of the resources are well-funded experiment, which I don't think it's how the OSG originally was. But still, we were able to run our Montecarlo campaign. So this is again, this is a summary of what we did in the past several months. As you see, we ran an average of about 400,000 hours per day. And we ran about an average of about 30,000 jobs per day. So this is, again, it's a summary of our computing on the OSG. Again, we are close to 72 million score hours with 24 million jobs. And this is to generate and at the end process 80 billion events, which are fully reconstructed. We thank Fermigrid, SUITS, and Atlas as they provided us with most of the CPU for doing that. So let me conclude now. So REDTOP is a proposed super eta and eta prime factory. It's designed completely to search for new physics below the GeV, but above the BeV, the MEV. It's a meson factory. And let me stress that every meson factory in the world, I mean, either a B factory, a Tau Chan factory, even a Phi factory, they all produce a broad spectrum of nice physics. So the eta prime factory is promising to do exactly the same. This is an only experiment which SHIP was approved only a year ago, I think. It took them 15 years to get approved. We also are struggling because there are few resources. We are now hoping that the European Spallation Service wants to host us. Otherwise, we will check again with CERN. But again, SHIP is the only approved experiment which is sensitive to all portals between the dark matter and the standard model. Now there is a eta factory in China. It's a cheap copy of REDTOP. So it means that REDTOP was really designed to perform. We can do a lot of nice physics, new physics, and also nuclear physics. In order to cope with the very complex signal and super high rate, we had to use a detector technique that's very innovative. And a lot of other experiments will benefit from that, not just REDTOP. On the other side, the beam requirements are modest, can be met by several laboratories in the US, Europe, and in Asia. Fermilab will be a perfect laboratory if they will decide to host REDTOP. Let me take the opportunity to thank the OSG collaboration for their, REDTOP exists only because of the OSG. The physics case was so complex, it requires so much computation that without the OSG, probably we won't exist. So a special thanks goes to Pascal. He has helped us in all possible ways. And he also Pascal designed the computing architecture for REDTOP. You can find more details, mostly on physics, either on our website or on our white paper on archive. And that's it for now.
Thank you. Corrado, I have a quick question. Is the Shita and the Chinese experiments approved right now? They're being built, or they're still also hanging about?
So they want to try to make a lot cheaper. So they're taking REDTOP and cutting corners. So they have something between 1 to 2 order of magnitudes less sensitivity than REDTOP. For this kinds of experiment, the detector is old. The bottleneck is not the accelerator, because you make billions of ETAs easily. I mean, LHC makes trillions of ETAs. The problem is distinguishing those mesons from the background. So they presented at the ETA factory conference in Sweden 2 weeks ago. I mean, the results are pretty poor, essentially, because if you go high in energy, you make a lot of ETAs, but you make even more background. So the Chinese can make 10 to the 14 ETAs. That's no problem. It's easy. The problem is distinguish them from the background. For that, you need a super fancy detector. So the Chinese detector is not as good. But it's only a matter of money, because we have published a lot of paper. I mean, everybody knows how to make a REDTOP. So at the moment, the Chinese wants to save money. They're presenting a cheaper design. They will make 10 to the 14 ETAs, but it's not clear what their sensitivity is. Was that your question, Pascal? I'm sorry, I can hear you very far away.
It's already done deal on the Chinese side where they're going to build this, or they're still debating?
Okay, so China works the other way around as the West. In the West, you have a laboratory, an existing laboratory, an existing collaboration forms, and decides that they want to do an experiment. So they do a lot of work to build the physics case for that experiment at that laboratory. And China works the opposite. They spent the last 15 years in building a laboratory, which is a fantastic, beautiful laboratory on top of a hill in southern China, overseeing the ocean. And the laboratory will be completed the next year. But when they started, they didn't know what to do with it. So about 2 years ago, they start asking around and asking, well, what are we going to do with this laboratory? And so the ETA factory was one of them. So they are now proposing an ETA factory, but it's almost sure that it will be approved. Basically, REDTOP has built the physics case for them. So the laboratory should have the first beam next year, but the has started designing the detector less than 1 year ago, so they are pretty late. But China has thousands of scientists, so I'm pretty sure they will be ready in 4 to 5 years.
We're having short on time. Any questions from the others? Okay, hearing none. Thanks, Corrado, for joining me.
Thanks for having us.
Yeah.